These significance tests, okay. All right, and this is just like the homework that you turned in. And the homework's posted for Wednesday. So let's look at this. Suppose a university claims that the average ACT score of their freshman class is 30. But we think the university might be inflating the scores, you know, for the US News and World Report ratings and so forth. Some universities have been known to inflate their scores. So we think the university may be inflating their average. So we're wondering about that. They claim that it's 30, but maybe it's lower than that. We think that it might be lower, but we don't have the resources to sample everyone in the population. So what do? Since we don't have the resources to sample everyone, what we do is we're going to take a simple random sample from the whole population, okay? And then we took a simple random sample of 50 students and found that their average was only 29.1 with a standard deviation of 4.5. So is this evidence that the university is really lying? That they bumped it up to 30 when it's really only 29? How would we know? Well, if we polled everybody in the whole, if we've got data on all the thousands of students, we could check their claim, but we don't have the resources to do that. How can we check it from just one sample of 50? That's the question. So let's think about this. It says formulate the null and alternative hypothesis. The alternative hypothesis is usually the interesting thing that you're trying to show. In this case, that the university is lying. The null hypothesis is the null, dull, everyday, just that the university is telling the truth, and that our sample just happens to be lower than what, you know, that the true average really is 30, and the sample just happens to be a little bit lower. So we have to formulate, the null hypothesis is always based on the luck of the draw. So we have to translate this situation into a box model, into drawing tickets at random from a box. So in this case, what we could see is that the box would have what? One ticket for every single person at the university. So it would be thousands of tickets. This is called the null box. And the null hypothesis is that nothing weird is going on, that there's a random draw from this box of 50 tickets, and we just happen to get 29.1, even though the average is really equal to 30. Just like the university claims, okay? So we draw from here thousands, we draw 50 tickets, you know, you draw 50 tickets, and we get an observed average, a sample average, equal to what? 29.1, even though this is the null hypothesis. So there's thousands of tickets inside this box, one for every student at the whole, is it just freshmen? One for every freshman. Oh, whoa. Okay, so I don't know, at this university it would be about 7,000. I don't know how much, it's just a large, we're not going to use this number, so it doesn't really matter, but thousands of tickets, on each is written, what? An ACT score. And it's one ticket for every freshman. Does everybody understand one ticket for every freshman? Do you all see that? And we're drawing 50 tickets out of here, and we get this average. Okay. So, what's the null hypothesis? The null hypothesis is that the university is telling the truth. That the average of the box, the average of, you know, this box, or the average of all freshmen, SATs, is equal to 30. The university is telling the truth, and that this difference that we see, this effect that we see, this 0.9 difference is just due to the luck of the draw. It's a small difference. And the difference between what? What we observed and what we expect is small and just due to chance. Okay? Observed average and expected average is small and just due to chance. So this 0.9 difference is small and just due to chance. Observed is just due to the luck of the draw. And the alternative is usually what you're trying to prove. The alternative is the unusual thing, what you're trying to prove. Like if it was a drug, you'd say the drug worked. It's not just due to chance that the people in the treatment group got better more quickly. It's because the drug worked. It's not just due to luck. The alternative is always that we're seeing some real effect. By real, I mean it's due to particular cause, not just due to chance variation. So the alternative is what? That in this case, that the average of all freshmen is really, that the university is lying, and that the average of all freshmen is really less than 30. That's why we see such a big difference in our sample, because it's really less than 30. The average of all freshmen is really less than 30. And that's why we see such a, they think this is a huge difference, such a small average. Okay? That's why we see such a big difference. Maybe that's an easier way to, I don't want you to get mixed up here. That way we see such a big difference between what we observed and what we expect. Okay? So they claim this difference is big. That's what the alternative says. All right, so that's basically the setup. Any questions on that? Or any questions on the idea of it? Okay, so now I'm going to have to get out my calculator because I didn't do this problem yet. Okay, so let's, all right, so how are we going to do this? Well, the idea is that you have to compute a z-score. And the z-score is what? The z-score is always your observed value minus your expected value. This is your observed value minus your expected value over some standard error. Okay? And what we observed is 29.1. That's what we observed in our sample. That's our observed average. These are all for the average because we're talking about averages here. Minus the expected, which is 30. Okay? All over the standard error for the average. And this is what I had to get my calculator out for. Now that is the standard deviation of the box divided by what? Do you know? The square root of n. All right, now first off, the standard deviation of this box, were we given that? No, we're not even sure of the average. So this is an unknown, and we're going to have to estimate this. We'll estimate from the SD of our sample, which you always have that because it's just a little sample, which is equal to what? That has to be up here somewhere. Oh, right here. So that's 4.5. So we're going to estimate that as 4.5. And you know what we're going to do in our next chapter, 20? We're going to see how if you have a really small sample, smaller than 50, a really small sample, that this estimate is an underestimate. It's not good. But we have 50 students, and so it will be pretty close. So it's legitimate to say 4.5. And then which n? What is n? It's always our sample size. So this is always the sample size, and we're going to estimate that. So this is what? 50. All right, so that's what we have to do, and let's do that. So we have 4.5 divided by the square root of 50. And what did I get? 0.6363. Okay, so that's about 0.64. That's what we'll put here. Okay? I could do it exactly here. And then on the numerator, so what do we have? So z is equal to, it's negative 0.9, that 0.9 difference, over about 0.64. And what do we get when we do that? You already did it? What'd you get? Negative 1.41. That's our z-score. Okay, so how do we interpret that? Well, remember that what we're thinking about here is what? We're thinking, okay, that in terms of z-scores, we always have a 0 in the middle here, but what we're thinking about is the sampling distribution of the average. If we did this over and over and over again, took 50 tickets out of this box, if the average really was 30, we do it over and over and over again, we'd expect 30 in the middle, obviously. And what this standard error tells us, where's our standard error, that we'd have 30, a z-score of 1 right here would be 30 plus 0.64, and a z-score of negative 1 would be 30 minus 0.64. Okay, well we have, let's just do our axis here. We have a z-score of negative 1.41. So that's where 29, this is negative 1.41. That's where 29.1 lines up, right there. We wanted to know how unusual it was. If it was far enough out that we could reject the null. So what is this? This is the possibility. This area right here, the area of the tail, is the chance that you'd see this big a difference, or even greater, if it really was due to chance, just by the luck of the draw. This is how often it would happen. What percent of the time it would happen that you'd see this extreme a difference? And so we should find out that area, and the way we can do that is we look on our table and we see between negative 1.41 and 1.41, right in here, that's what the table will give us. And hold on, see if I have a table with me. This should be one in the exam. Yeah. Okay, so between let's look up 1.41. Okay, so that's about 84. Okay, does everybody agree that's about 84% in the middle? Yeah. So let's put 84% in the middle here. That means 16 is on both tails, but we knew the alternative was that they'd be lying in the, if they were lying, we knew they'd be inflating. We knew what the alternative was, that it would be less than. So here is our tail, and that is 8%. And that's what's known as the p-value. So p is 8%. And remember, very small values of p are evidence against the null. That's something really weird. If it would only happen once in a blue moon, if it's really a small percentage, if p is small, then we say that couldn't be due to chance. It's probably due to a particular cause. In this case, that's not, the convention is that when p is less than 5%, we reject the null, and here p is not less than 5%. So we think, 8% of the time we would see such a big difference, so it's plausible, it could be due to chance. We're not ready to reject yet. That's just the convention, okay? So what do you conclude? Well, p is equal to 8%. So what do we conclude? So we conclude that the university, usually the language is that it's plausible argument. We don't have it's plausible that the average ACT of all freshmen is 30. We don't have enough evidence to convict, basically. Think of it as a trial. We have to make some decision. We don't have enough evidence to convict, basically, to say the university is lying. Our P is not beyond a reasonable doubt. I'll just use the language of the legal language. Our P is not beyond a reasonable doubt. That's a reasonable doubt. It's plausible. It would have to, in other words, P is greater than 5%. That's what we call, if it's greater than 5%, we're saying there's a reasonable doubt. It's not beyond that. RP, it would have to be less, RP is greater than 5%. So we're not beyond that cutoff. All right? Do you understand? It's very similar to our legal system in terms of the logic of the argument. We assume innocence. We assume the null-dull hypothesis that the university isn't lying. And then we've got some evidence, but it's not enough for us to convict. Okay? So that's the idea. Why don't we say we accept the null? Why do I use this negative? So we conclude we can't reject the null as the language. Can't reject null. That's the language you'll see when P is greater than 5%. Now that double negative is confusing. Why don't we just say we accept the null? Well, you could think accept the null, but people don't do that because in the same way we haven't proved the null because we assumed the null to begin with. In the same way with our legal system, if we let somebody off, we don't say we've proved he's innocent. We just say we can't convict. You know? We're not saying for sure he's innocent, like in the OJ case, there's a lot of evidence, but it wasn't beyond a reasonable doubt. So the jury, from their point of view, said they didn't think he was innocent. They just said, we can't convict. Yeah? Oh, how do we know if it's with or? Very good. For this question, it would be, it's a very good question. How do we know when we're setting up these box models whether they're with or without replacement? Whether we're drawing tickets without replacement or with. Well, in this case, we're drawing 50 separate students. It's like we're taking a sample. So it would be 50 tickets without replacement. It doesn't affect our standard error. We don't have to use the correction factor because 50 is a small percentage. But how do you know when it's with replacement? Okay, well, can I borrow your notebook for just a second? Oh, here's somebody's notebook. The same rules apply as apply in that box model summary that you looked at. So let's just check that out for just a second. And I'll turn to it here. Okay, so this right here on page 201, it's the same idea. When we modeled when you do with and without replacement, for surveys, it's always without replacement. And this is like a sample survey when you're taking individual people out of the box. When is it with replacement? When the box model is based on like a guessing game, like for the ESP one. And not just sampling, taking a few. Do you know what I mean? Does that help you, whoever asked the question? Okay. All right. Yeah, if it's like a guessing game. Okay, so any questions on that? All right, I think now we're going to, let's just look at this review for just a minute. And, okay, so what are we going to do now? Well, we're going to do a variation on the z-test, a refinement, basically, of the z-test, and it's called the t-test. How many people have heard of t, or the t-test? Raise your hand. It's very, very widely used. And what it does is it gives you a little bit more accuracy when you have a small sample size. Okay, it gives you just a little more accuracy. So if I look back, remember what I said, this is what it takes care of. When you don't know what your standard deviation is, and you have to estimate it from your sample, I said, this estimate's pretty good. This estimate of 4.5 was okay, because we knew N was 50. We were drawing 50. But let's say we only drew 3 people or 4 people. Let's say we only drew 4 people out of here. Then this estimate of the standard deviation wouldn't be a good estimate. It's going to be too low. And so let me show you what I mean. Let's go to, so we use something called the t-test. And there's kind of an interesting story behind the way the t-test was developed. Let me get, hold on, I've got to find that chapter. What did I do with it? Okay, so here it is. So now we're on chapter 20. And there's kind of an interesting story behind this, the t-test. It was developed by this guy named Edmund Gossett, and he was the quality control engineer for the Guinness brewery back about 100 years ago. And his job was to taste the Guinness beer. You know, Guinness, that dark, you know, Guinness stout. You're probably all familiar with this beer. And they're very proud of their beer at the Guinness brewery, and his job was to make sure that the beer was good, that there wasn't, so what did he do? He couldn't obviously, so he took small samples of the beer and tasted it to make sure it was all right. And obviously he couldn't sample huge amounts, he couldn't drink all the, you know, lots, because he'd get drunk. So he just took little tastes. Only about samples of about 3, maybe 3 little tastes from, you know, a huge vat, let's say, of beer. And the idea was that when he was doing this, he was supposed to reject the beer if it was, let's say the perfect taste was right here. Let's say that was the perfect taste that they wanted, and they know that the average follows the normal curve. Well, he only had 3 things to average, let's say, or 2 things to average. And at that time, everybody assumed that even if you only had a very small sample, that it would follow the normal curve, and, you know, 0 would be right in the middle here, and the perfect taste, I don't know, he has some score, this is the perfect taste that he's aiming for, and it can't be too bitter or too whatever. And they said, okay, he should reject, let's say we were only doing a 1-tailed test this time, let's say he should reject when it gets to 5, when the area, whatever, you know, it's so far off the average that this area right here, this is 5%. That's when he should reject the beer. And what happens then? It's sent back for more tests, that batch of beer. Not, you know, they take a bigger sample from that. So that's what he was doing. But then what happened was he wasn't rejecting 5%. He was doing everything right. You know, this was he's doing everything right. When would 5% be? 5% would be when there's 90% in the middle. So what would our z-score be? When do we, what would be? I think it would be 1.65, okay? So when you got a z-score, whatever matched up, whatever, you know, the bad, at this point, he rejected the beer. You don't have to write this down. Okay, but then what happened was he wasn't rejecting at 5% of the beer. What was happening was he was rejecting something like 15%, a much greater percentage of the beer. And so the supervisor took him aside and said, hey, Guinness, hey, Gossett, what are you doing? You're rejecting more than 5%. He says, well, I'm doing the math correctly. And they said, well, we don't know. And it turns out that when you have a very small sample size, like he did, you have fatter tails. So it might look like, I'll exaggerate it, it might look more like that. So he was rejecting an extra percent. He was rejecting a lot more than 5%. He was rejecting all that area. And they didn't know, this is called, so this is the t-curves. This new curve is a t-curve with fatter, and this is the normal curve. And it has fatter tails. So how did he discover this was going on, what he said was, hey, I'm going to take a break and figure this out because I'm a very careful person and I know that I'm not doing anything wrong here. So I'm going to take a break. And this was before, obviously before calculators, and what he did was he took a box model. He had a box model, and he sampled from, he put tickets in the box with numbers on it that corresponded to all the possible tastes that he could get from the beer. And then he took a sample of 3 from that and plotted the distribution of the average, the sampling distribution of the average. And what he got was that it didn't, these t-curves that didn't follow the normal curve. And you can see here, they depend on your sample size. So, the smaller your sample size, like here are t-curves with different degrees of freedom. That means 1 minus the sample size. So for example, if your sample size was 3, like his was, that has the fattest tails. See? But then if you get up to 20 degrees of freedom, which means a sample size of 21, well, it's hardly distinguishable from the normal curve. It's this one right here. So there's a series of t-curves. There's not just one t-curve, like there's one normal curve. No, there's a series of curves depending on your sample size. So that's one, so he discovered these, and he also discovered that the standard deviation of small samples underestimates the standard deviation of the whole population. And that makes sense, because if you just take, let's say, 3 numbers and average them, this is assuming you don't know the average of the whole population, and you don't know the standard deviation, you're estimating from a sample of 3, well, your standard deviation is going to be based on the average of just 3 numbers in your sample. So it's going to sort of be, and the average, your samples are going to follow, the standard deviation of your samples will follow those different averages. So it's going to be less spread out than if you took the average of the actual population. Another way to look at it is, suppose that you have some real extreme values in the population. You're unlikely to get those real extreme ones in a small sample. It's another way to look at it. So it underestimates it. Okay, so the idea is when you have a small sample, and why don't we just say less than or equal to 25? A lot of people make this, a lot larger, but for our purposes, in this course, we're using a lot of approximations. We'll just say less than or equal to 25. Okay, then if you have a small sample and the histogram of the contents of the box is close to normal, it doesn't have to be exactly normal, but pretty close to normal, and you don't know the standard deviation of the box, you just know the standard deviation of the little small sample you have, then you use t. Okay, so we're only going to use it in problems where we're trying to estimate the average, where we're looking at the average of a box, problems that involve averages and not percents, because percents wouldn't be close to the normal curve. And also, we already saw the standard deviation of the sample percent is very close to the standard deviation of the population percent. So we're just going to use this. So why don't we say we'll use t only for problems, only for average problems, not percent problems, not problems where we're dealing with the percent. Okay, so like the problem we just had, we could use it if it was a small sample size, or the ones, we'll look at some problems, we'll review an example that we did previously in a page or two. Okay, so let's look at this. Small sample, how can you remember this? Close to normal, unknown SD. So this says small, this says close to normal, this is an unknown SD. Unknown population, or box SD. We always know the S, and we only know SD of the sample. We always know the SD of the sample. It's a tiny little sample. So we could just figure that out. Okay, then use T. Okay, so then use T. And I have sort of a negative opinion of the way that T is overused in intro stats courses. T is used when the sample size is much larger than 25. In fact, they just basically don't, even when it's a huge sample and it makes no difference, because it's much more tedious to do these T curves and you lose your intuition. It's extremely like the idea is just like the normal curve. So I have a negative opinion of how widely T is used in intro stat to teach statistics. And so this looks like a dirty word to me. Snut, like a nasty word, slut, smut, snut. So that's how that's how you can remember it. Okay? So when it's a small sample, and you're probably, believe me, you should be grateful that I'm not teaching it the way everybody else teaches it, where you start right from the get-go with this complicated formula for standard deviation, where you divide by n minus 1 to find an average instead of n, and then you have to use all these different T curves, and you lose all your intuition. Okay, so think of this as snut. All right, that's when you use it. And the most important, the one that usually you have to pay the most attention to is this unknown population, SD, the unknown SD. Because you can tell right off the bat if something's small, and usually, if it's really far off from normal, people aren't going to try it. You know, you'll never use it with a percent problem, for example. And so that's how it is. So if you have a small sample and drawn from a normal population with an unknown SD, this is it, S-N-U-T, snut. Okay? So what if the population isn't small? Well, then we can use Z, right? And what if the contents of the box is really far from normal, like zeros and, well, then we don't use either. We use something else which is beyond the scope of this course, okay? We'd use the binomial distribution if it was zeros and ones, the exact, like we did a little bit of that with, but for now, let's just, don't worry about it. And this is the one that's really, if you know the standard deviation of the population, you can just go ahead and use Z. Don't worry about it. But you usually don't, so that's the most important one. Okay, and here's the T-curve. So let's do an example. And so you have to make, so when you use these T-curves, you have to make two adjustments. You have to increase your SD just a tiny bit. So instead of using the standard deviation, you use just a little bit bigger than the standard deviation. If you were doing it from scratch, you would divide by, when you take all your deviations and take the average of them, you wouldn't take the real average, you'd take an average with a little bit, one less. Like if you had 5 observations, usually when you take an average, you divide by 5, right? You take all your deviations, divide by 5. No, you divide by 4, which makes it a little bit bigger. But if you're given the SD already, and you want to change it to SD plus, like the situation you'll usually be in, well then you multiply by this factor right here, and you can see that factor is, I mean, that's basically doing the same thing. It's canceling out the n that you used in your denominator, the square root of, you know, canceling that out, and instead dividing by n minus 1. All right, so this is always what? When you do this right here, that's square root of n over square root of n would be 1. You're dividing by a smaller number, so this is always bigger than 1. All right, but it's bigger than 1. The bigger n gets, the closer it gets to 1, right? I mean, if n was 2, you'd have 2 over 1. Square root of 2 is 1.4. But look what happens when n is like 26. Let's do that. That would be the square root of 26 over the square root of 25. And that's just a smidgen. bigger than 1. So at this point, I decided for the purposes of this course, we're going to cut it off at 25. So when n is 25 or less, we'll use, or less than 25, let's just say less than 25, we'll use t. That's what I said in the, is that what I said here? Is that what the cutoff? Yeah, less than or equal to 25, okay. If it's greater than 25, we'll use z. Okay, now, so let's just do an example that we did before. This is an example from the first example we did. It was from chapter 20. It was the one that was based on this true experience I had where I thought this TA that taught the early 8 a.m. section was better. And I thought this better than the other TAs, and I thought that the 8 a.m. students were more serious so that they'd have a higher average on the exam. And it turns out they did have a higher average, but I wasn't sure whether it was due to chance variation or if it was real. And if you look back in your notes, I didn't bring my notebook, but if you look back in your notes, we saw that it was a difference of between 75 and 70. That 5-point difference turned out to be very significant, right? Now let's just do the same problem, but what if we only had, let's say the section was only, instead of 36 students, like that problem was, let's say it's only 16 students. Now that we have the small sample, let's see, a large lecture has 1,000 students. This is the same example we did way back when, on the first day of class, not the first day of class, the first day of this section, back from the exam, we looked at this example. And a large lecture has 1,000 students. On a midterm exam, the class average was 70 with a standard deviation of 12, and the scores followed the normal curve. It suggested that the early morning section had more serious students and would therefore have higher scores. When this section had 36 students previously, I said it had 36 students because it was modeled on what really happened to me. Suppose we only had 16 students and their average was 75. The question is whether that 5-point difference is strong enough evidence for us to think that it's not just due to the luck of the draw, that those students are really different in some way. They really are more serious or their TA is better. So now I have to decide because, the sample is small. So we have a small sample, small n, only 16. Should I use the z or the t? Is it normal? That's the next thing I'm going to check. Is the population inside the box? Inside the box, do we have a close to normal? Let's check. Where does it say? Oh yeah, we do. Okay, so we check that off, And do we know the SD of the box? Do we know do we have an unknown SD or not? Do we? Unknown SD. SD is equal to question mark, or do we know the SD inside the box? We know the average is 70. Did I give you the SD? Oh yeah, it's 12. Oh, we don't have an unknown SD. So what can we do? We can unknown SD? No. We know SD, so we can use Z. Okay, so we can use Z. This is exactly what we did back, I don't have my notebook with me, but it's exactly like what we did back the first example in chapter 19 was this. Okay, so what are we going to do now? Well, what do we know? So we want to know the null hypothesis is what? That the difference, that 5-point difference, was just due to the luck of the draw, right? The difference between the observed and the expected is small. That 5-point difference is small between 75 and 70, and just due to the luck of the draw. So here's our null box. If it was just due to the luck of the draw, what do we mean? Well, we have 1,000 tickets in here. On each is written an exam score, and we know that the average here is 70, and the standard deviation is 12. All right. And then what did we do? We drew a random sample. We have an n. Our sample size is 50. And it was without replacement because, no, not 50. What is it? What is our sample size? 16. Our sample, we took 16 people. The idea is that this section, if we randomly draw 16 people out of here, yeah, we get an average of 75, but that's just, so what? That's small. Between the observed and the expected. The observed average is 75. Our expected average from this box is obviously the same as 70, and that this 5-point difference is small and just due to chance error. Okay, and the alternative is I thought there was going to be a big difference here, and I was testing to see if there was. I thought there was going to be a big difference because I think there's something. It's not just due to the luck of the draw. That 5-point difference, the difference is too big to be due to chance. It must be due to some particular cause. That 5-point difference is too big. It would only happen once in a blue moon. It's too big to be due to chance. It must be real. It must be real. Okay, so now what do we have to do? To find that out, we have to compute a z-score. So we say z is equal to the observed average minus the expected average over a standard error. And that's, we observe 75, we expect 70 over the standard error for an average, which is SD over the square root of n, which is going to be 12, we know that, over the square root of 16 instead of 36. Last time, if I had it here, I could show you, but I don't. You can look back in your books. What did we get last time? We had a 36 under here, so we got a 2. 12 over 6 is 2. Now we get a 12 over 4. So this is 3. So this is 1.67. Well, when we got a z-score of 2, we had 5 over 2, 2.5. And we were way out on the normal curve. Now we're not so far out on the normal curve. Where are we? We expected to get 70, and now 75 is not way out here at z-score equals to 2.5. It's only a z-score equals to 1.67. So that between 1.67 and negative 1.67 turns out to be 90.5%. So that's between 1.67, which is where 75 lines up, and negative 1.67. That is, so this area right here, this is our p-value, this right here. And that says p is 9.5 divided by 2. So that's 4.75%. So what do we do? If we have the cutoff is 5, that arbitrary cutoff, then do we reject the null? Yes. Small values of p say, oh, that's really unusual. So if we had to make a decision based on that p equals 5, we would reject the null. And say we have strong enough evidence to reject the null and conclude that there is something that it's unlikely to be due to chance. Okay? That there is a particular cause. Reject the null because p is less than 5%. We don't have nearly as strong evidence as we had with a bigger sample. When it was 36 people, it would be very unlikely to get an average that far away. And if we just had a few people, of course you could get an average that far away. And you'd have a very small z-score large p. All right, now let's just do the same thing, but what if we don't know the standard deviation? If we're going to have more uncertainty. That's our next problem. I just wanted to show you the same problem with different numbers changed, with different numbers. So now we're going to do exactly the same problem. Normal, we have the small. We only have 16 students, but now SD is unknown. So we use T. We have an unknown SD. We have a box here where we think the average is, we know the average is 70. We're drawing out how many tickets. N is only equal to 16. But now we don't know this SD. And we have to use, here's our observed average is 75, and our sample, our observed SD, the sample SD is equal to what? 12. But we don't know the box SD, and we cannot estimate it as 12 because the sample size is too small. So we have the exact same thing. The null is what? That the 5-point difference is small and just due to chance. And just due to chance, it's the same exact thing, due to luck. And the alternative is, the 5-point difference is too big to be due to chance. It must indicate something real is going on. So the 5-point difference is too big to be due to chance. There must be some other reason, something else going on. I just wrote luck instead of chance, okay? Now, so what happens here? We're still going to do this t statistic that's going to be like z. Let's skip down to here. We're going to have our observed minus our expected over the standard average, standard error for the average. This is going to be the same. Our observed is still 75. Our expected is still 70. We still have that 5-point difference, but this standard error for the average, this is going to be bigger. We're going to have more error because we have more uncertainty. This is going to be bigger. How do we make it bigger? We make it bigger because we're going to not use, before we did SD over the square root of n. What are we going to do now? We're going to use SD plus. So this will be bigger, which means our t will be smaller. So it says we have to go further out to reject the null, okay? So let's look at this. So we have, all right, so compute SD plus. That's what we have to do that. We have to estimate. We can't use that. We have to estimate SD a box with n less than 25, less than or equal to 25, we need to use SD plus, not SD. You need to use SD plus. So we can't use 12. We have to make 12 a little bit bigger. So SD plus is equal to what? Square root of, what's n? 16. What's n minus 1? That's going to make it bigger. You see, that's bigger than 1. Times what? 12. So instead of using 12, we have to use something a little bit bigger than 12. And this turns out to be 12.39. This is what's going to go here. 12.39 SD plus. Okay, that's the main difference there in our calculations. And then we're going to use the t-curves. Okay, so instead of doing this, we have to do, instead of doing 12 like we did before over the square root of 16, and we got 12 over 4, so we got a 3. Now we're going to get what? We're going to get a little bit more than 3. We're going to use 12.39. So that's going to give us a little bit more than 3. We'll have more error. This is your error. Just think, T, you have more uncertainty. You don't know the SD, you have more, so you're going to have bigger error. So you're not going to have 3, you're going to have 3.1. The standard error using SD plus is always bigger. Okay, it's always bigger than standard error using SD. All right, which means our t is going to be smaller because we're dividing by a bigger number. So now our t is only 1.61. So t is always smaller than the corresponding z. We did the corresponding z and we got what? 1.67. Now we get 1.61. So that's one change, okay? So this is our, okay? Now we have to do the other change, and that's we have to use the t-curves. Yeah, okay, so I'll just So this is what we're doing here. So what should we write? T is less than Z because SD plus is bigger than SD, and you're dividing by a bigger number, so you're getting something smaller. So we only have 1.61. Even if we use that as a Z-score, we wouldn't get, if we used it as a Z-score, we're going to get what? It's going to be closer in, so we're going to get more, P is going to be bigger. But it's going to be even bigger because now we're going to use the T-curves. So now, remember, there's a family of curves. There's not just one curve like there is with the Z. There's one curve, there's a different curve for each sample size. But they don't call it sample size, we call it degrees of freedom. So what is degrees of freedom? It's the sample size minus 1. So what does that even mean? The degrees of freedom is equal to the sample size minus 1. So in this case, it's 16 minus 1, which is 15. Basically, with the degrees of, do you know what, have you ever heard that term, degrees of freedom? Raise your hand. Basically, we're trying to calculate the standard deviation, right? And because we have an unknown standard deviation. Now, if I gave you all the deviations but one, you'd know what the last one has to be because the sum of the deviations is always what? The sum of the deviations always has to add to what? You know, the positives and the negatives cancel out and they always have to add to 0. Do you remember this? Well, if you, so if I gave you 15 of the deviations, you'd know what the 16th has to be. So we say that 15 of them are free to vary, but the 16th one is determined. Because if you know one less than the deviations, if you have 10 deviations, you only need to know 9 of them to know what the last one is. So we have 15 degrees of freedom. Okay, so find P by using the T-table. All right, so we have to use the T-table. So turn to the back of your notebooks. And I don't have a notebook with me, but can I borrow yours? Okay, so we're going to look at the, oh, you have it in your notebook. Wow, I didn't remember, I never did this before. Okay, so it's in your notebook here. Wow, okay. Very nice. So it's right here. I copied it. This is the first semester I've done. My back is so bad that I can't even lug a notebook to class, so that's why I'm just carrying this. Yeah, I'm in pain. Okay, so here we have, look at this. All right, so from this point on, right here, you're going to reject the null. Okay? You'll reject the null. So we have 15 degrees of freedom. We're right here. So we'd need a T. Where's our T? Our T equals, what is our T? 1.61. So it's right here. It's not, this tells you the p-value right here. Okay? This tells you what T you would need in order to reject the null. We'd need one as big as 1.75. The more degrees of freedom, the lower that number gets. Remember, for the normal distribution with a one-tailed test, it's 1.65. Then you'd have 90 in the middle and 5% on that side. So here it's 1.61. So no, we cannot reject the null. We would need what? We would need a T greater than or equal to what? 1.75 to reject the null. To reject the null. We don't have enough evidence. We don't have enough evidence. Because we had more uncertainty. We don't have enough evidence to conclude that something besides chance is going on. Something besides chance is going on. In other words, there's a 7%, this is about, P is about, what do you want to say, 7%? It's anywhere between 5 and 10 I'd accept, but it's about 7%. So we cannot reject the null, all right? And the evidence isn't beyond a reasonable doubt. That's all I can say. So in this case, we had more uncertainty, so we're not rejecting the null. Okay? All right, if you have a question on your own exam, come see me. Thanks. You're welcome.